why we don't have telescopes orbiting every planet yet. The concept sounds like science fiction, but it's grounded in solid engineering. You could absolutely station telescopes in orbit around other planets and relay their data back to Earth through a network of communication satellites. In fact, we already do a miniature version of this on Mars. NASA's Perseverance and Curiosity rovers don't transmit directly to Earth. They send their findings to orbiters like the Mars Reconnaissance Orbiter, MRO, or the European Space Agency's ESA Trace Gas Orbiter, which then forward the data home. The relay system works beautifully, cutting down on power requirements and allowing rovers to focus on science instead of constantly pointing antennas at a moving target 140 million miles away. The advantages of planetary orbit telescopes would be staggering. A telescope orbiting Jupiter could capture cloud dynamics, aurora, and moon activity with a clarity Earth-based instruments can't touch. Atmospheric turbulence ruins ground observations, and even Hubble, sitting just 340 miles above Earth, has to work around our planet's orbital position. Put a scope in Jupiter orbit and you're sitting ringside, able to watch Io's volcanoes erupt in real time, or track storms on Europa's ice shell with meter-scale resolution. The same logic applies to Saturn's rings, Uranus's tilted magnetosphere, or Neptune's mysterious dark spots. Proximity matters enormously in astronomy. So what's stopping us? The brutal economics of deep space missions. Launching a telescope to Mars takes about 7 months and costs hundreds of millions of dollars. Getting to Jupiter requires gravitational assists and multi-year flight times. NASA's Juno probe took 5 years to arrive. Saturn is nearly a decade away. Cassini launched in 1997 and reached Saturn in 2004. Building and operating a telescope is expensive enough on Earth. Doing it across the solar system multiplies the costs by orders of magnitude. You need redundant systems because there's no repair mission if something breaks. You need plutonium power sources for the outer planets where solar panels become useless. You need a deep space network, DSN, with enough capacity to handle data from multiple distant assets, and NASA's DSN is already stretched thin. Current deep space missions as of August 2026 include NASA's Artemis lunar program, continued Mars rover operations, and preparations for the Europa Clipper mission, scheduled to study Jupiter's moon Europa. The James Webb Space Telescope, JWST, positioned at the second Lagrange point L2, about 1 million miles from Earth, represents the current gold standard for space-based observation. JWST's infrared capabilities have already transformed our understanding of distant galaxies, exoplanet atmospheres, and star formation. But even JWST, despite its revolutionary design, remains relatively close to home. Extending that capability to every major planet would require political will and budgets that dwarf current space science spending. Then there's the solar gravitational lens concept, which makes planetary orbiters look quaint by comparison. Einstein's general relativity predicts that massive objects bend light, and the Sun is massive enough to focus light from distant stars in a way that could theoretically image exoplanets with absurd precision. The focal point begins around 550 astronomical units, AU, from the Sun, about 14 times farther than Pluto. A mission to that distance would take decades with current propulsion. Voyager 1, humanity's most distant spacecraft, has been flying since 1977 and only recently crossed 160 AU. But if we could station a telescope at the solar gravitational focus and aim it correctly, we might resolve features as small as 10 kilometers on a planet 100 light-years away. That's continental-scale geography on alien worlds. Research teams at NASA's Jet Propulsion Laboratory, JPL, and various universities have published feasibility studies on solar gravitational lens missions, though none have moved beyond the conceptual stage as of mid-2026. The relay architecture itself is the easy part. Data compression, error correction, and multi-hop transmission are solved problems. The Mars Relay System proves we can build robust interplanetary networks. Future human missions to Mars will likely expand this infrastructure with additional communication satellites in Mars orbit and possibly relay stations on Phobos or Deimos, Mars's 2 small moons. Commercial space companies like SpaceX and Blue Origin have expressed interest in supporting NASA's Artemis program and eventual Mars colonization efforts, which would naturally expand communication capabilities. China's space program has also been developing lunar relay satellites for its Chang'e missions and has ambitions for Mars exploration in the coming decades.